like to begin this last lecture with an additional remarks about an additional remark about neuromorphic functions. So we call what is a neuromorphic function. So we call the definition. Up to equivalence relation, you have a covering of X. X is a Riemann surface by open sets, of course. They cover X by open sets. So you have some, it could be a plane domain, it could be a Riemann surface, it could be something terrible. But you have open sets, say UI and UJ, two examples of open sets of this covering. So open sets, usually I write UI. And on UI, Mi equals Fi over Gi on UI, where they're holomorphic, and Fi and Gi are holomorphic. And you would be, it's possible, if you're unlucky, that F and G were both 0 at the same point. That would be rather bad. But then you could cancel, as you know, you can cancel the zeros, so we can holomorphic, and we can assume and relatively prime. That means Fi equals 0 at a point implies Gi not equal to 0 and vice versa. Or Fi Gi 0 implies that Fi is also not 0. So that we can always assume just by cancellation that they're relatively prime. And they're defined locally. And you have the compatibility condition is that Fi, so you write Fi over Gi equals Fj over Gj, but you don't want to write that on Uij. You can write that, but the good way of writing is so you don't write quotients, you write Fi Gj minus Fj Gi equals 0 on Uij. That's the setup that we can always assume. And then there's an obvious thing that's wonderful. What's wonderful is, instead of all this stuff, we simply go to homogeneous coordinates, Fi, Gi, in two variables. Now remember what that means. That means, I mean, I can write the upstairs space. I can think of that as being in C2 minus the origin. But what it means in non-homogeneously, this means that it's equal to 1 Gi over Fi, and we go to the coordinate Gi over Fi when Fi is not equal to, when you can divide by Fi, and it means that you can, when you can divide by Gi, so it's Fi divided by Gi, 1, which gives you the coordinate, this is maybe the coordinate, if I can divide by the second thing, that's what I'm calling Z, so this would be the zeta coordinate, and if I can divide by the first thing, divide by yeah, this is zeta coordinate. If I can divide by the second thing, this is where GI is not equal to 0. This is the z coordinate. Right? And z equals 1 over zeta. So you pay your money and take your choice. It's capitalistic. You just decide which chart you're going to use, and that chart that you're going to use depends on what's 0, what's not 0. So you know, what you get here then, that you can verify easily yourself, that the meromorphic functions on X is isomorphic to the holomorphic maps from X to P1. Isn't it true? If I have a holomorphic mapping from X to P1, I can write it in homogeneous coordinates and get this stuff. And if I have a meromorphic function, I can do this. It's purely formal. But I think this is a very much better place to work. So this is a very better place to work. Just the holomorphic maps from X to P1. So let me just comment now a little bit about modern history. An example that we just discussed was X itself being P1. So this means that meromorphic functions here are this amounts to the study of holomorphic maps of P1 to P1. And now another word for that is let's take a map here. Let's even say it looks like this. Map P1 to P1. And another way of saying this is P is a holomorphic self-map. Self-map of P1. Maps P1 to itself, it's a holomorphic self-map. Now, I will talk about the simplest case in a minute, but I want to talk about a slightly complicated case. For example, in the z-coordinates, you can write it in the z-coordinate, for example. For example, let's write something in the z-coordinate. The most famous first example that anybody studied was this. So just z squared plus a constant. That is a stupid map. My 7-year-old grandson can understand this map, maybe. But since it is self-map, you have v, you have phi squared, you apply it to itself. I mean, phi2 is phi composed with phi. Since it's a self-map, you can compose it with itself. So phi with itself 3 times, and so on. Right? Repeated process. Everybody here knows about applied sciences, that in applied sciences, you have dynamical systems which come from repeated processes. Right? This phi to the n is an example of a holomorphic dynamical system. Not so long ago, these dynamical systems, even that simple-minded system that you have up there with z squared plus a constant, the analysis of this began with some computer pictures of important sets, important related sets. Sets where that arise in the theory of dynamical systems are very famous. These sets are called Mandelbrot sets. For example, Mandelbrot's. This guy, who is not a mathematician really, he knows a little bit about mathematics, decided long ago, from the point of view of computers, long ago, to make computer graphics of the phenomena that are associated with these things. And made very beautiful, interesting pictures to discuss the dynamics of this dynamical system. Even this one, which is interesting, surprising. Okay. So let me just mention my colleague and friend, Igor's, Gorbovikis, professor here now, young professor, will give a course next semester. I sent it around, maybe you saw, in holomorphic dynamical systems, and he is a specialist in this area, and he will tell you about exactly this kind of phenomena if you're interested in. Okay. I think all three specialization courses are very, very interesting, but he is a specialist in this area and will tell you all about it. So I wanted to mention that. Okay. Okay. So that's the case of P1. And now automorphisms of P1. And this is a little bit devoted to Crystal because you were asking about automorphisms of domains in P1 and so on. These are holomorphic self-maps. And of course that's P1 to P1. But it has to be invertible, of course. Right? If it's an automorphism, it has to go both ways. So obviously, if you square something, the inverse of this thing is a square root. It's not going to go both ways. So you're in big trouble if you have higher degrees. So these things are going to be of a low degree. In fact, these are exactly, this is exactly, phi is a degree 1. And what that means is that homogeneous coordinates are mapped to linear guys. Otherwise, if you have higher degree, it will not be the case. Oh, I'm putting Z1 and Z0 here that I want to try to remember. I don't see any reason to put 0. I'm sorry. I fell back into my old habits of notation, but like that. Sorry. Okay. And that's the homogeneous way. And then if you want to know what happens to Z, so you divide by Z and see what happens. Z1, Z2, now what is Z? Z is when you divide by Z2 not equal to 0, so you divide by that, and so that's Z1 divided by Z2, 1. And then the coordinate is Z, which is Z1 divided by Z2. And now this thing goes to this homogeneous stuff there. I have to dehomogenize, but I'll write this down first. Z1, Z2, C, Z1, Z2. And now I'll divide everything in sight by Z2. And so I get this equals A, Z plus B, and C, Z plus D. And then I'll divide this into that. And I get A, Z, B over C, Z plus B, wherever it makes sense, wherever it makes sense. You see, I better not divide when that's 0, so I mean, there's certain places you better not do it, wherever it makes sense. Okay, so what it says is that if you have a matrix A, B, C, D, that's defining this mapping as linear stuff. Watch this, you just apply to Z1 and Z2. So this is a linear transformation of the upstairs space. Just forgetting that homogeneous coordinates is stupid, homogeneous, who cares? And we map the upstairs space to AZ, just as you do with a matrix, right? That's really the mapping, right? It's really the linear mapping. And of course, it should be an invertible matrix. So this matrix should be invertible. Should it be inverted? Otherwise, this mapping will not be invertible. So this matrix would better be invertible. All right? So that's why we talked about this before this came up, and I had this in my brain, and this is the way this thing. In this form, I never understood this when I was your age. This is called a linear fractional transformation. Linear fractional transformation. I never understood this. Linear gebrochene Transformation. It's just a translation of the German. And the subject was very German in the beginning, so I think this is just a translation. But what it is, it's just a matrix. Right, there it is. Yeah? And so you have a mapping from GL2C C to the automorphism of P1. And this is a surjective mapping because every automorphism is given by this. It has to, if you're going to have an inverse, it has to be a degree 1. So this is a surjective mapping. Every automorphism arises in this way. It's a triviality, really. Okay. And now this is some mapping. I don't know. Let's call this. I don't know. I have many names, but this is called the big feet for fun. All right. And as you fans of group theory know, that if you have a mapping, it might have a kernel. All right? Right? And it's, you at least did very nice work on talking about this kind of thing. I appreciate your work. So let's look at the kernel of this thing. And it's easy to see that this kernel is just a diagonal matrix. It's completely obvious. If you multiply this thing by lambda and this thing by lambda, you get nothing because it's homogeneous. You just check that's what it is. Okay? So this is just C star times the identity. Right? So that's in the kernel. And so as you see, you have an idea. You may choose instead of GL2, you may choose the determinant of this guy just by choosing this diagonal thing. Determinant of this ABCD to be 1. You get it? I can just multiply by the right lambda here and make the determinant 1. Right? Because yeah. So what that says is that that you have really a better thing from SL2Z. SL2Z means determinant 1. When you see this in the literature, S means you made the determinant 1. Okay. So this mapping is also surjective. Let's call this mapping here the new mapping phi hat maybe. Right? And then you say, because Iglesias told you to do this, you better look at the kernel of this guy. Right? So you look at what is the kernel of this guy? So the kernel of this guy is still around. It's terrible. There's a big problem because plus minus 1 has still determinant 1. Right? So plus minus the identity is the kernel of this thing. It's not a very big kernel, but it's a kernel. Right? And as another way of writing this is the finite group of order 2, which is, right? So what we better do to get things right is that the automorphism group of P1 is just SL2C, so determinant 1 stuff, modulo plus minus the identity. And that's what at least tells you to do, mod out the kernel. That's what we talk about in the work. Mod out the kernel, you get an isomorphism. And this has a name in the literature, it's called the projective special linear group. And the reason the P is there is projective, and the reason it's projective is P. So this is the group, there it is. And that's a wonderful group of automorphisms. It's a wonderful group that plays a big role in mathematics. Yeah. That's interesting. That's very interesting. And now I come to the last problem 4. Now remember, I stated 3 problems before. And I unfortunately am a very slow lecturer, so I am not solving any of these problems, but I'm still connected with Jacobs University giving this intersection course, and I will come to visit Jacobs University during the semester, next semester, and give 1 lecture on each of the problems. So I will come 4 times. I need to talk to Prabhat because he needs to do his thesis. So I will give 1 lecture on each of the 4 problems that I've talked about, and I've talked about 3 problems so far. You may recall what they are, and I will explain how they are solved, and even state what the correct results are, and explain how they are solved, each in 1 lecture. Of course, I cannot give all details because these problems are non-trivial, but you will have some idea of them. And I come to the problem 4, and that's the last thing I want to talk about in here. What's the basic topological information about P1? If I'm asking you on oral examination this question, you should say, well, Professor, you're stupid. You should not ask it about a complex manifold because topology has nothing to do with the complex structure. You should ask it about the underlying topological manifold, whatever it is, or differential manifold. So you should say, what is the basic topological information about S2, 2-sphere? Right, we have forgotten, when we use the word topology, we forget complex structure. We forget. Okay, and so we draw a picture of it and we look at it for a long time. And then you say, well, let's think about the loop space. Let's think about loops in here. Let's take a base point. Let's think about loops in here. This is a loop, and this is an optimistic loop because you know that loops could fill the space, right? You could fill the space with loops. But I told you can look at least piecewise smooth loops is good enough for the fundamental group, and you can just see that you can contract a loop to any base point. So you see that the fundamental group of this thing is P1, is trivial. Fundamental group of this thing is trivial. When I write groups, I write 1. I write the fundamental group is trivial. I emphasize that as a much finer statement than the genus is trivial. Remember, the genus is the fundamental group modulo the commutator group. That's how you get the genus. Right? It's 2 genes. That's interesting. The fundamental group is trivial. Fundamental group is trivial. Fundamental group is trivial. Why is that interesting? Well, Riemann knew this. I'm going to explain the answer why this is interesting. Riemann understood, and then the successors in topology understood, that you should study the theory of covering spaces. And and I'm going to give you a 10 or 15-minute lecture on covering spaces and why this fundamental group being trivial is so important, okay? So there's some word called covering spaces. The basic results about covering spaces is the subject of algebraic topology. Algebraic, but I find it very geometric topology. Okay. Ready? Here we go. We already had an example. We had the example of the ramified cover let's take the example again. I'm just going to beat you over the head with this example. Z1 cubed plus Z2 cubed plus Z3 cubed. This Fermat thing equals X over P1. By now you can dream about this. I've said it so many times, right? So there were the ramified cover looks like this. Here's P1, and here there were 3 ramification points. So I'm going to put them in here. I put in the points, 3 points here, and now let me tell you the notation. In the base space, the points in the base, well, above this we had. At these points, it was 3 to 1 locally. Remember? It's 3 to 1 locally here, these points. I don't know, maybe it's 3 to 1 locally at these points. At these bad points where it's ramified. Otherwise, there are 3 points in every fiber. I'm not very precise, you don't care either. Otherwise, there are 3 points in every fiber. And so the interesting points upstairs, in my notation, the interesting points upstairs are the points upstairs, and the points downstairs are called B. Okay? And the easy way, they're called branch points, and the easy way to keep branch points and ramification points straight is B means base. Okay? I mean, it's a question of notation. This is my notation, it's the same notation many people, but not everybody. So this is a ramified cover, and it's a ramified cover, and you have 3 ramification points. And now what Riemann said is what you ought to understand first is without the ramification points, so take them out. Take them out. Okay, why not? Take them out. This is after removal. So this guy here is a ramified cover. And this other guy here is unramified. So remove B and all the points over B. Over B and X. And there's a big warning here. In general, if you could have the following situation. You could have, for example, I don't know whether it's possible or not, you could have 3 branch points down here, and it could be 2 to 1 right here, and 1 to 1 up here. So you see this is 2 to 1, and then in general it's 3 to 1, and then maybe here it comes together 3 to 1. Right? And then maybe it's again 1, maybe it's again 2 to 1 here, 1 to 1 here. You see what I'm saying? The bad fiber is where there's some ramification point in the fiber. So what you do is you take out the base point here, the branch, and then you take out these points here. And once you get all these things, it's unbranched. Right? It's unbranched 3 to 1 unbranched cover. Okay. So we study unramified covers. Okay. That's the first thing to study. And this idea was the idea of Bremen. And he didn't have a theory of covering spaces, but he understood it, of course. And now the theory of covering spaces, this is what's usually meant by covering spaces. So let us say that we have Y, topological space, and X over Y. Get used to my level of abstraction. I think we've talked to Nicholas about this. You have X over Y. And then you should draw a picture. I mean, later on, here's Y. And then the thing is, if you take a small enough neighborhood here, I'm going to call this mapping pi for projection. If you have a small enough neighborhood here, like we do there, we have, in this place over here, I would have 3 things above this. So I would have 3 things above this, but maybe I have 100 things above this, and maybe I even have infinitely many things above this. I'm going to make that precise, but yeah, okay. So I'm going to make the precise statement, and I'm going to tell you what every student in the world makes as the first mistake. Okay? So every Y in Y has a neighborhood U equals, I'm going to call it V. V equals a neighborhood of Y, so that pi inverse of V is the disjoint union of neighborhoods UI, so we would have here's V, and then upstairs we would have, you can't count them, there's no natural way of ordering them, U1, but well, you could have some artificial way of counting them, but you can so maybe infinitely U1000, and so on. So this is a disjoint union of these things, and the key thing is so that pi, the projection restricted to UI, is a mapping from UI to V, of course, is a homeomorphism. Yeah, so that's what we had over here. We had three upstairs, and here's V, and here we have these 3 things. And each time we can choose a coordinate here, so this is just a homeomorphism. This is biomorphic. But this is just topological spaces, so this is homeomorphic. You get it? So upstairs, you have many points, but locally, it's a homeomorphism around each one of them. Now here's the mega mistake. I guarantee you, I have refereed many papers where this mistake was essentially the only mistake in the paper, written by serious mathematicians. If I take one point out here, for example, there, this is no longer a covering space. Okay? Because the mapping from this U1000 down to V is no longer a homeomorphism because it's not even surjective. There's nothing lying over this point here. Right? The mistake is that things that look like coverings are not coverings, they have holes in them someplace. And this is a mistake you will make if you're not careful, I guarantee you. Okay? So this is a covering space. This is an elementary thing, a covering space. Okay. Yeah.
But those ramification points that we had, they're always, I mean, if you take the pre-image of that, or if you look at it above, they will always coincide. So we don't have a point where, like if we take out one point, like we always gonna take out the point of all three lines, and not just.
I think I know what you're saying. In this case, it's ramified here but not ramified there.
Mhm.
Is that what you're saying?
But still, we're gonna take out all of them.
But still, I'm going to take them all out because if I just took out one, I would have exactly the problem I was just talking about,
Mhm.
right?
So if we take out all of them, then we have our.
Yeah, that's what you really have to do. You have to take out all of them. So you have all the images downstairs and you just take out a pre-image of everything and then you got it. Yeah, you got it exactly right. Thank you. Okay? This definition is trivial, right? So this is called a covering space. And now, the basic, I would say, a priori, fantastic, in this positive sense of the word fantastic, fact. Fantastic fact. Fantastic in the sense, the American sense of the word fantastic. You know, Americans go, Donald Trump goes, make America great. But and Americans use these words like this, but I'm an American, so I use the word fantastic. This theorem is fantastic, that I'm going to tell you, in the American sense of the word. You see in the word fantastic, the word fantasy. I don't mean that. I mean it's fantastic in the American sense of the word fantastic. I love this theorem. And this is what we learn in mathematics, to look for something universal. And it's called the universal cover. The universal cover, there is something that's universal that many people, also the Americans in these churches, they talk about God coming down and doing things for you. Hey God, hey man, come down and give me something universal. This is wonderful, God. Thanks, God. He gave us this. The math God gave us this. Yes, the math God gave us this. It's this. If you have a Y, there is a unique covering, and you have to say what unique means, but it's up to obvious homomorphism, blah, blah, blah. There's a unique covering here, such that for any X, which is a covering, there is a covering of X. Everything factors through some universal cover. There is one cover of any manifold. It is called the universal cover of that manifold, so that any other covering factors through this manifold. It is called the universal cover. Believe me, it's not hard to prove. So for a proof of the existence and uniqueness of Y, so existence and uniqueness, of course you can read any topologist's book, but topologists tend to write stuff that's too complicated for simple-minded people like complex analysts. Maybe take a look at Riemann surfaces by my good friend and whom I admire greatly, Otto Forster. He's older, but he's still very active in Munich. He's really a man from southern Germany, so if you Germans know what that means, he's really a Bayer. He's a wonderful, you know, but a very democratic, very wonderful man. I like him. And in that, he gives exactly the description of this thing. Now, yeah.
So we say that pi is our covering, so that the map between x and y is the covering.
Yeah. So let's even formulate. Okay. There is a universal mapping I will call tau. This line of this thing has nothing to do with that. There's a universal mapping tau, such that given a pi, there is a mapping tau hat here. Okay.
So it's
So,
the tau.
let me write it. Let me write it slowly. There exists a universal mapping tau so that given pi, there exists a covering y hat down to x with above diagram commuting. So with tau hat, so with tau hat followed by pi equals tau. Alpic doesn't like, you think I maybe had the wrong order here, possibly. I don't think so. Everything factors through the universe, that's what we say, everything factors through the universe.
So what is in our covering space?
It's some manifold.
No, I mean, so it's the covering space is the space of all universal matrix tau? Or
No,
coverings phi?
again, no. Let's say it slowly. This is worthwhile. Given, let's say a manifold, so there's no danger of topological spaces and so on. Given a manifold Y, there is a universal, canonically defined covering space, which I call the universal cover of Y. Here. That's the first thing. The property of this universal cover is, you give me any other covering space, all possible things, I don't care. It factors through it. So it's universal, that it really somehow comes, it's intermediate. Any other covering space is intermediate. You see, this really intermediate here. This goes down and down. So any other covering space is really just intermediate to the universal cover. Now, Optic has a better, once you're having the feeling, the intermediate idea is a very good feeling, right? Yeah, okay, I like the feeling of intermediate. Does that help, Nicola? Intermediate.
Let me see. I mean, so the covering is, okay, tau is our universal mapping, but that's not our universal covering, actually. Tau is not the universal.
This thing here, what is a covering space? A covering space is a base space, an upstairs space, and a map.
I see, okay. Now if you have, and now the mapping from y hat to x would also be another
Covering space.
space, and also the one from x to y.
That's right. So given is something from x to y, there's something from y hat to x to give you the commutative diagram. Yes, it could not be better. This is one statement, but I thought you were going to ask, and I think that's what you're going to ask. Tell me about this y hat. What are the properties of y hat? What characterizes y hat? Right? You really ought to know that guy. That guy is so important. You really want to know what y hat is, right? Okay. It's a good question. There is a precise answer to this question. That's the amazing thing. The precise answer is the y hat is simply connected. We call this simply connected. Fundamental group is trivial. The y hat is characterized by its fundamental group. This is a wonderful thing, right? It says, yeah. So given y, there's a unique covering, and it's unique with this property. So the question is, given y, what is the simply connected cover? Question. given y, comma, what is the simply connected space? This means simply connected. We call this simply connected. This is, you have to understand, it's a stupid word, we don't understand it right now. Simply connected space, y hat, so that with covering y hat to y. You got it? Well, first property, you start looking at properties. And this you're going to love. The fundamental group of y acts freely and properly, I've talked about this, on y hat, so that y to y hat to y is simply the quotient y hat goes to y hat modulo the fundamental group. Remember, we talked about what it means in group action. You have the orbits of the group. That means the picture of this thing is you stand downstairs, and this is downstairs in y. You have this covering of all this stuff here. These points go from here to here, from here to here, from here to here, and so on. These points are just orbits of the polygon. These are orbits of the group. Orbit, 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 orbit. You quotient out the orbits, you get y. That's wonderful. It could not be better. Okay, that's the first remark. Property 2. If, for example, y hat is a Riemann surface, is a complex manifold, then so is y. I'm sorry. If y is a complex manifold, then so is y hat. And the transformations are acting here are holomorphic, are acting as holomorphic transformations. That's a lot at once to swallow, I know, but let me repeat it. This is just maybe motivation for you to learn a little bit of elementary topology. It's a very, very important subject. There's a good German word here that you need to learn. You ask these German guys. I like this. This means summary, but in a nice, strong sense. Fazit. Sounds like, yeah, this really brings everything to a point. Maybe you can say summary, I don't know what you say. Don't you feel Fazit when you hear the German words a little? Here's what you need to think about. Here's it. Yeah. It's just like my student, I told you about this, who a very nice, very brilliant woman, mathematician. She invented the notion of Merksatz, which means it's a Satz, a theorem, and Merk means something you could remember.
Yeah.
Merksatz. This is the thing you want to remember. Facet. This is the thing you want to remember. You start with y, and it looks like this. There's something called y hat, that everything is determined by y hat. It's incredible. Everything factors through y hat. It means that if you have something downstairs, you can localize the thing downstairs, and this pre-image is a bunch of things like this, maybe infinitely many, and these things are homeomorphic, and the identification that identifies these points along the fiber here is the group action. Pi1 acts, the fundamental group acting on this thing. Okay? And this action is free. That has nothing to do with being free to democracy. That means it means a non-trivial element really moves something. The non-trivial element is free. It doesn't have any fixed points. Nothing fixes anything. It could not be better. This is a free proper action on the universal cover that gives you everything in life. It gives you everything in life. Believe me. It's universal. It could not be better. And this thing is acts. This is facet. Free, freely, and properly. That's what you want to keep in mind. Now, example. Remember, this is characterized by the property that the fundamental group is trivial. Question. What could happen in complex analysis? In one-dimensional complex analysis. That's what we're doing in this class. In other words, what could y hat be? Well, I mean, you should try to find it, right? And so you look for examples. Look for examples. And the first thing that occurs to you see it's simply connected. So I mean, simply connected means the fundamental group is trivial. And so you have the idea, you're very optimistic, we were talking about this with various people, you have the idea that y hat is equal to P1 because that's simply connected because that's nothing other than S2. That's simply connected. That's a candidate, right? So you should start with a candidate you know, right? Then you look at a transformation, AZ plus B over CZ plus D. That's a general linear transformation, a fractional. And the trouble is, this can have a fixed point. And the reason is, if you just bring this over here, I don't know, I don't have the courage to do it right. AZ plus B equals C, CZ plus D. You get a quadratic equation and you solve it and you get a fixed point. Right? It says that every transformation, bihomomorphic transformation of P1 has a fixed point. It's a trivial fact. But this says that it can't act freely. Because I said freely means no fixed points. Okay? So this implies that no free action and this implies y hat only occurs, okay, it occurs when y hat equals y. Because you have no free action. Okay. So you look for other examples. That was example, this is example 1. And example 2 is another example you have, which is certainly simply connected, is y hat equal the complex plane. That is certainly simply connected. You can contract it. I mean, it's obviously simply connected. So that's really a candidate. So I just write it here. That's really a candidate for being the universal cover. Yeah. And you check, which is an easy exercise, that if phi is an automorphism of this thing, automorphisms are automatically proper mappings, so they extend across infinity to be automorphisms of the Riemann sphere. Then, in the usual z coordinates, phi of z is az plus b. That's an affine transformation. That's an automorphism. You just check, that's it. That you can't have any other. Okay? I have to watch out. And you see that if A is not equal to 1, then fixed point. So the only candidates are the form z goes to z plus, and I'm going to write a letter here that I've used before, omega. That's a translation by something, and maybe we have translations by two things. So you either get periodicity, in this case, just omega 1, so n omega 1, that would be just one variable, or n1 omega 1 plus n2 omega 2. These would be the only possible ways the fundamental group could act on the universal cover here, and you either get C star here, as we know with the exponential map, or you get a torus here. That you can check as an elementary exercise for, I mean, you can do this. You don't need it, it might help to do this. Okay? Where you need my help, and now I have to quit soon, is, and problem four is, what are the other examples? P1, not interesting. Complex plane, interesting, particularly because you have tori. Other examples. The amazing theorem, and this almost defines complex analysis in one variable, is there's only one other example. Can you believe that? There's only one other example. Let me say it very strongly. P1, none. Complex plane, okay, you got a torus or something. One other example. Only one. And you know it. When I was in high school, there was a song by a guy named Sam Cooke, who I really liked to listen to him at nighttime in bed when my mother wasn't watching. So this is only, and his song was "Only You and For You Alone." I remember that. If I try to sing it, it'll make you sick, so I don't do it. Okay? It is. This is an amazing theme. and only one other example, and that means that every Riemann surface, except for these here, every Riemann surface is the disk modulo an action, a free proper action of a group of automorphisms. Now that is so false in general, higher dimensions. This is somehow almost a definition of complex analysis in one variable. That really the only interesting universe is, so the disk is y hat, and this group this is a discrete group that you understand in certain ways. And these are connections to many subjects, and one of the main things here you connect to with this point of view is what is called analytic number theory. And I would say if you like this point of view of just reducing everything to a disk and then thinking about this gamma and so on, then you should look at the books of Siegel, Carl Ludwig Siegel, his Göttingen lectures shortly after the war, after World War II. He's a great German mathematician at that time. By the way, he was in Frankfurt, and then he left Frankfurt during the war, and he watched out to make sure people in Frankfurt were not in trouble. And then after the war, he ended up going back to Göttingen, going to Göttingen. And so this was a wonderful mathematician, and I know indirectly a wonderful lecturer, and of course a wonderful author of, in this case, 2-volume series. So there are connections to analytic number theory, and the connection is in this group. So on that highlight, that's this course. I just told you there were 4 major problems. I could go through them again, right? On a non-compact Riemann surface, you can solve any problem. And that's the reason for that, from a global point of view, is a certain solution of a partial differential equation. Yes? On a compact Riemann surface, you have the theorem of Riemann-Roch, which allows you to solve in a satisfactory way the question of, I call it the Mittag-Leffler problem, the question of whether or not principal part is the principal part of a meromorphic function, and many other things, the theorem of Riemann-Roch. And then the theorem of Abel, which tells you precisely what the points the divisor has to satisfy to be the divisor of a meromorphic function. And then the 4th problem, it's not a problem, it's a statement of this theorem here, which is called the universal, this theorem is called the uniformization theorem. The statement is the only simply connected domains are the V1, the complex plane, and the disk. Now, you have in the history of mathematics some really important steps, but this is one of them. Okay, this is one of the guiding steps starting with Riemann. In case you're interested, it was proved by a German mathematician by the name of Köbe in the 1920s. His proof is probably not complete. I think the modern proof that is complete is due to Alfors, who's my doctor grandfather, so I'm proud. I don't care. I hardly met it. So thank you very much for coming.